Alrighty then. All right, we got a clap, half-hearted as it was. All right, Merry Thanksgiving Eve, everybody. I should be, I should be just getting back in my old stomping grounds on the East Coast. However, there was a little minor mishap. Recap last Friday's episode. It's okay. We don't need to dwell. Yes, I know I'm dwelling. That's okay, but we'll let folks start to roll in here because, as always, or usually we don't want to say all-encompassing statements, especially if we're unsure about them. Because remember, my friends, only Sith deal in absolutes. At least that's the word on the Star Wars street. But I digress. So, all right. So we got some. Well, this is mostly the stuff from yesterday and everything. So I'll erase that. But today we're gonna continue onward as we were wrapping up yesterday. We were talking about bases for reality, or AKA the ingredients that make up where we live. Okay. Yada yada yada. The measurables that we can actually measure. And coincidentally, you can make up reality from just five of them. Yes, my friends. Like like the platonic solids, there are five ingredients of reality. Coincidence? Well, that might be up to the observer. We're gonna have to see how it plays out because you just want to say, it's just a coincidence, or but it's like is there a little more? I'm just saying, there only have to be five of them. Technically six in four dimensions, which is a very interesting thing because I think you get most everything, and I think 24 cell. I think it's the 24 cell is the bonus one aside from the simplex. The tesseracts. I have to always remember it because I was introduced to that concept through Marvel and Loki. He's stealing the tesseract. Oh, what is that? It's a four-dimensional cube. Da-da, da-da. But oh yeah, and then you have the octahedron. Uh, octahedron, uh, icosahedron, and dodecahedron. Coincidentally, the 600 and 120 cell are the hypericosahedron, the hyper dodecahedron, basically the four-dimensional equivalents. They happen to be dual to each other, and at least within professional work that's been going on that I know of, at least Nick from over at the Wolfram Institute, he found that the 600 cell happened to be quite nice for modeling qubits. Yes, go figure. I know. Imagine my shock. Oh God, I got to get him on sometime. I need to stop being lazy about that stuff. Hey, welcome, Rick. Happy Thanksgiving to you, or Merry Thanksgiving Eve. But so what we're going to be going over today is, let me grab myself a marker from over in the bin. All right. So we're going to be talking about Planck constants. As we talked about before, we have five-dimensional ingredients. Those dimensional ingredients are, starting with our bottom turtle, which we're going to put on top here. Fine. All right. And we got spaints, but we're going to express that as a dimension of length. And we're going to go to electric charge, and we're going to list it as a generalness charge. I'm in quite a good mood because we started to listen to Professor. Does he even teach, or is he just on? He teaches. He teaches. Professor Jacob uh, Brendanary. Uh, long story short is he's been saying this for possibly the past couple of years. But recap real quick. Apparently, he was teaching some like introduction to physics for like first year's physics students, and he wanted to just give them just a taste of like quantum mechanics and quantum theory and stuff like that, just at the end of the year. Um, and apparently he was looking at things. He's like, I couldn't do something. He's like, okay, here's what I'm going to do. I'm going to focus on. We've got our like classical mechanics over here. All right, and we got the realm of the quantum. Ooh, over here. And he's like, all right. there's a chasm in between them. He's like, oh, let me just follow that chasm, and we'll see the point where okay, it gets narrower, and we can just kind of like hop across it. To his surprise, apparently the chasm just kind of it just kind of ended. He's like, what? Keywords for that is apparently he didn't necessarily know any better, and apparently, due to his not knowing, he did not assume a very core axiom was that you need to use non-Markovian dynamics, matrices, however you want to formulate it. And basically, rather than being stuck to an infinite dimension Hilbert space, he's like, you can totally have your infinite dimension Hilbert space. Whatever configuration space you want, you can basically have. But apparently, he did. No, we assumed Markovian dynamics. Sorry, if you do non-Markovian, basically the past kind of matters. That's the general gist of it. Uh oh god, if I ever have him on, I'm gonna have to do the pleasantries and everything and be like, sir, why did you take all the fun out of quantum mechanics? Now, I'm not qualified to say that or anything. I never sat down and was just like, let me absorb all of quantum theory. I did not do that. But if it just happens to be that one of the underlying assumptions we didn't actually need, and we broaden our degrees of where we can actually work that will stick up to all the other stuff and things that we formulate. He's like, well, basically, it would take you now have a broader space of configuration. Basically, he used the terms uni-stochastic. So I would, if that's your thing, Kurt has a interview with him on the Theories of Everything channel. But if you actually want to dig deep into it, when he gave a couple presentations at I think the Foundation of Physics Harvard YouTube channel, one of Harvard's physics channels, Cambridge. If you just type in his name, uh, it's fascinating. So I'm very biased on it. I totally want it to be true because I'm like, oh yeah, it ends up being just the product of Cartesian planes and stuff. I'm like, wait. So it's the product of something? Hmm. That might bode well for some of us. Now, tangential rant aside, uh, hey Keisha, thank you for joining my friend. Oh, we got Trina. Trina, I missed. Wow, you were here before me. I am a terrible host. I apologize. Where are we at? Oh yeah. Our dimensional ingredients. All right, so we got our ingredients. Oh my god, I can't even spell. All right, whatever. Is what we'll do. We've got our stuff. The stuff of reality. Okay. These are the things that we measure, basically, with all the constants of nature, 288, which may or may not be a coincidence, depends on what you necessarily consider a constant of nature. But we got at least 288 predictions or retrodictions, because some of them are already hitting the number, but then we got more significant digits. So go experiment. All right. We got time. We got space expressed as length. We got electric charge as charge. And we got mass. Yes. I'm made of a bunch of that stuff. And then we got temperature. Makes stuff hot, at least to observers like me. Okay. At least I have corresponding base units. What are the base units? Well, it's a reference. When you're referencing each other, these are equivalent ones. So basically, time, we use them as Planck units. So it's basically just going to have subscript p. So we just have little t because it's like 10 to the minus 44 seconds of t sub p. Got length, and that's L sub p. Charge, we use Q for it. Why? Because that's what we do. You got Q sub p. Mass, we got M sub p. Are we detecting a pattern, anyone? When we get down to temperature, since it's 10 to the 32 Kelvin, that's freaking, poof hot. Yeah, that's big T, sub P. Okay. When these dimensional ingredients combine, we get the stuff and things of reality. You just have to express them in different forms, different powers, different combinations. But fortunately for us, or at least me, I can count to five, usually. Okay. So why am I showing? We've done this before. Those of us that have been paying attention and have been here, basically here, or at least checking up on us. Um, this, I think, is a very key point. There's only five things, five dimensions of measure we need to construct reality. WTF, mate? Because from these, if all of a sudden we combine length and time, we get speed of light, or the maximum length you can go per, or the maximum length you can go per minimum unit of time. Okay. We got charge. Charge, some people may disagree. I believe this is the one of charge, the maximum expression of charge for a thing. Okay. Could be wrong. Mass is a maximum expression of mass of a thing. Temperature is a maximum expression of temperature. Wait a second. Min, max, max, max. Wait a second. Hasn't Thad talked about that? Maybe there are some internal actions in that crazy diagram that even I'm still trying to parse and everything. But it's basically all right. You got time, you get your bottom turtle. All right. Imagine a circle. Circle does this little thing. And it's going as it's clockwork. Length's going to start to turn. And then once you start to get inside out, you get to an outer expression. You get an expression of charge. And then charge goes right in there with mass and everything. And if you do the whole uh, calculation for charge and everything, if you have charge one and charge two, and that's over r squared. Basically, if you just put in the Planck units there, you'll get the Planck force. But then when you do the whole, you have to have like Coulomb's constant and stuff there. And then when you do that same thing with mass, and you do mass one, mass two, and you have your big G and everything there, and you have it as a Planck length squared, you get the Planck force as well. What? On the Planckie scale, charge equal. Well, I mean, we're saying they're ones anyway, so we would expect that to be the case, no? Okay. Temperature, hot. Hot. 10 to the 32 Kelvin. You're uh you're gonna have to have a very special set of circumstances for that to really be the case, because can't really have matter as we know at the boiling point of matter is like what is it? About 10 to the 12 Kelvin. Something like that. That's why you need to have diffusion, other stuff and things. Something principle of least action. To my knowledge. But Rick is commenting that time and energy, yep, building blocks. Oh, mass, energy, temperature, entire buildings. Ooh, I'm very inclined to agree with that. Yeah, that's stuff with the frequency charges. Okay. All right. You can have seven charges. Okay. Um, then I have to think about that and actually probably follow some data. It's very intriguing. But okay, so that's that. That's not why we're here. Perhaps actually, to be fair, that probably is why we're literally here. But I digress. I digress. All right, so let's just bring up a little bit of stuff for the class right now, shall we? I'll bring this up just because I have it in a window right here. So I'm more than hopefully just another crazy person. Okay. Okay, so what is this? These are the claimed. These are what Thad found when basically, okay, the whole point of the log is I'm going to claim logs are useful. Why do I say this? Because if you take something, very often you raise it to, if you have E and then you raise it to something, you're essentially going to get whatever that something is out in another way. It's basically a self It's the, how would I say it? The minimal, it's like a relationship factor because like kind of like pi is a relationship to the diameter of a circle. Basically, E is the logarithmic relation of a given thing. So let's just do this real quick. We'll do boom, boom. We'll duplicate this. Okay, so if I do something like E raised to 5. Okay. All right, so we get that random number there. Click on this random number. And to nobody's surprise, if you take the log of that, you should get, oh, look, it looks like about 5. Okay, so that's essentially the relationship. Whatever you do, you're going to end, whatever is e's raised to, you can use as a logarithm, and logs are very useful because you can like add and subtract them. And then somehow it seems to magically work as like multiplication. They're useful. I'm sure there's some mathematicians out right there that have just got the pitchforks out. It's okay. I will do more to deserve that very shortly. Okay. So why the heck am I showing you this thing here? Okay. This expression, it comes out here. Oh, I actually need to reload this because we're going to want to show the digits. How did we get to this? Okay. So for instance, let's look up code data H bar because that's our good friend there. Usually comes up. Let's go back to Planck. We're going to go based upon the best of our measurements and calculations and the good folks at CoData. All right, go to the Planck time. Here's what we're going to do. Here's the formation. The formation is this. All right, we're taking those digits. So here's the claim. The magic, the voodoo, if you would, that we do in order to get this, we make an assumption. Okay, we're going to do E raised to that string of digits. Okay, we're raising it to literally the digits right there. Why? Because maybe if we had certain assumptions, and again, could be wrong, but maybe if there was something to that, remember, this is at the 44th power. The absolute magnitude of that is 44. We got a 44 magnitude. So if we go in there, let's say, all right, what if it was equal to 44? You could also do it as like, what is it? Yeah, basically the derangements of 5. You could do this here. That basically gets you 44. Okay. All right, so we got this expression. What the heck good is that? Well, the claim is we can find geometrically logarithmic based closed forms for that. What the heck does that mean? That means we solve for x. Because remember, something to a log is going to have that. And if we have different powers of magnitude and it's just reflecting more or less the same thing, and maybe we can slice it in different ways. Again, this is just a method that happens to be used. And all right, so what happens? We get out some numbers. What's the number we get out? We get out the solution right here. We click on it. I misclicked on it. I didn't even know you could still do that. Okay. Oh, wait a second. What's this friend right here? Pi hyperbolic sine squared of 1/4. That sounds like a very geometric thing. So if you take that and, okay, so we have it this way. So is it pi sine? That has it notated as that, but you can basically just do this. You can go, go in here, boom, deal our friend. And then we paste our friend over here. We can set this equal to 44, just so there's no confusion. All right. So then what we do is we take that geometric action, we multiply it by e, and then we solve for this. What are we looking for here? Oh, well, let's see. All right, so we got something equal to 44 something, like a 44 magnitude. Okay. And we got here, we got something here. Oh, it's giving us a real solution. Good. We like real. Wait a second. Please hold on. Give us more digits. What is this number right here? 5.3912, 5.3912. It's error 60 there. What type of magic is this? This is magic that may or may not come about when you really focus on something. You really are looking for an answer. You have the time and ability to think about it, and maybe luck. Being born at the time we are, where it's like, well, I don't need to write a letter to like Max Planck from like have it go over the ocean, have it take weeks, have him read it, have it to go to the library, follow up all these things. Hope he has the recent journal publication. Dude, there's literally a magic box. Like literally, like this window is a box that I could just seek out information. I can click on the symbol. You can see its definition right there. Oh my God, it literally is freaking magic. Um, so remember, my friends, any sufficiently advanced technology is indistinguishable from magic. Okay. All right. So that was a little thing. It, again, I'm not saying it's right. It's just if one were to look for additional information, because why is this whole thing important? The reason it's important is because right now, mostly when folks talk about constants in nature, You'll you'll hear about our good friends, the speed of light. You'll have H bar over here. Why? Because we have up to 9 and 10 digits. We only got most of these to like five. The Planck charge isn't even listed on code data. It is on Wolfram, and again, we do have a deviation. We may have a reason for that. We will get into that at some point. Uh, but we're using these because we have more significant digits. So we're trying to compute things. Now, as we were talking about yesterday, maybe something really interesting happens once you go, I don't know, 1, 2, 3, 4, 5, 6, 7, right around here ish. There seems to be something going on. And then from the good professor, uh, Barondess, um, he's saying that, all right, you might have your beables and your emergibles. And the emergibles might just be a combination of different beables potentially. So I'm like, wait a second, that sounds very familiar. Okay. But the whole point of this is if we happen to have these guys, the building blocks that literally make up our friends here, if we actually have the building blocks out to say as many digits as you want that you can throw into a computer and stuff, um, again, we only may need 14 significant digits. That's the extended tree R, and then from there, I don't know. There be dragons. Maybe there's already dragons. I know Joe Rogan is a big fan, and there may be some folks in the chat that agree. But I'm a scaly, so I'm biased. But if we had more significant digits of these, then might we better be able to predict and use these as scalars, so to speak? I'm using the quotes there because scalar, it can't be, it's not supposed to be a vector, and charge is charge usually seems to have a generalized way it wants to go, but I could be wrong about that. But these other guys, you can at least use as general scalars, to my knowledge. I think Wolfram Alpha Lissa is a scalar, but I'm like, well, actually, no. I think current has a direction. Okay, so I might just be wrong about being wrong, or I'm just wrong. But I'm sure one of those applies. Okay, but the whole point is, if you could actually get a lot more significant digits of these, if we get a higher confidence out to as far as we want for our measurements, as we can actually measure, might we be able to make better predictions? Might we have a better idea of what's actually going on? And when we have a better idea of what's actually going on, might we actually better be able to construct technology to make humanity better? Rather than the occasional totally not a leak and not done on purpose futuristic nuclear arsenals. It's like, Antimatter bombs? Question mark. I, listen, if there's a big rock heading towards us, listen, you can do what you want, protect humanity. But it's like, could we focus building on like, I don't know, cool technology, get true post scarcity, maybe, and people not go hungry, yada yada yada, because we have all the power we need. There's no more excuse. No, there's literally no more excuse. Okay, pardon me. I'll need to caffeinate up as I decompress from my slight rant of the world. Now, okay, we can erase our friend over here. Point taken. Okay. So as we saw for time, we did a whole bunch of voodoo, and the voodoo we got out was, hold on, let's go back here. Boom. All right, so the magical voodoo that we did was, all right, so it's pi. Oh, that's that circle thing. Hyperbolic sine of h squared, and that's multiplied by 1/4 or 1/4, and then we multiply it by e. We're solving for the digits of x up here, and we just set that equal to 44. The magnitude of that, and then that gives us our little thingy out there. Give us 5.391 times 10 to the minus 44 seconds. Cool. All right. All right. Maybe that was a fluke. Maybe that was just a fluke. Maybe there's nothing. Hey, there might be better answers. It's if we can find, if anybody can find better answers or anything to help explain some of these things, maybe it'd be a little bit better. Oh, yeah, it is the year of the dragon, isn't it? Yeah. I'm a rat. I was born the year of the rat. My brother was born the year of the dragon. But all right, let's go back. Oh, geez, what a terrible YouTuber. All right, what am I just bring up a random chart? Okay, so all right, we did that thingy before. Let's go back. So what's the thingy we're doing? All right, we're doing our extremely complex, aka you can put this into like a calculator. The calculator usually, aside from Wolfram Alpha, usually doesn't spit out cool closed forms. I'm sure there are other products that do, that I just don't know of any. Let's go back to our friend CoData. Let's go back. We did time. Let's do length. What do we got here? Let's again take our little hack, because remember, my friends, it's some people may get offended, but it's okay.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Roolead. I don't think it rules them all, and it might be just hyper Ruleo turtles all the way down.
Yes, it's on the back of an infinite number of hyper Ruleo turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
I love that clip. I love that clip. I remember when Jonathan was working on. I just so much fun memories, and then it's like Steven's like, do you need more processing power for what you're doing? Because he had just said something about how he had just gotten a new computer and he has like 168 cores or something. And Johnson is like, oh no. I do most of the stuff on my MacBook Air. And the chat just starts losing their minds. It's like the outrage of hacking the universe on a MacBook Air. I'm on a MacBook Pro, full disclosure. We want to be as open and transparent as possible, right? All right, so we do our same little magic trick. We do that. E raised to the string of digits with a Planck length. Yep. We're solving for x, but what's this magnitude? This is 10 to the minus 35. All right, so that's 35 orders of magnitude. Following our same little recipe, we type 35 in there. And we solve for x. What x do we get? We get this x over here. All right, let's click on it. Let's see what we got. Is there anything cool? We might need to search a little bit. Let's see. Oh, I don't know what to see. If there is another answer, it might be this. What's that? That's the goat constant, the goat ratio. So maybe it's that. Oh, they might be adding some new things here. Ooh, that's also pretty. But that's not what we're currently using because we're trying to follow something. What do we have our first one? So we had some signs. I don't know. Maybe we want something very geometric. See if there's anything else. More forms. Go. That goat thing is tempting. And that's also tetrahedral based. See, we might need to go a little further there. I think this one. Oh. What we got? We got. Oh. Cotangent of 1/7. That's a pretty geometric thing. Oh. Okay. So I think Thad rewrote it as just sine h of sine h. Well, let's just see if this actually does its little thing here, shall we? Let's delete that. Oh, take this. Cotangent 1/7. What's cotangent of 1/7? Cotangent 1/7. Oh, look, it's the number we had there. So we could also write that as. Let me just make sure I'm not just babbling nonsense. Okay, maybe I am babbling Oh, that's what we're. Sorry. Oh, the wrong part. Let's see. Love a bargain. All right. Oh, I'm a noob. Yeah, it's the same thing. It's just a -1. How dare I not make it inverse? Such a noob. But we can just do cotangent of 1/7. Why? Because that's easier and shorter, and I can remember that. All right, cotangent of 1/7. Oh, yeah, that's right. We're trying to do something. We need to multiply by e. We're solving for x. And what's the magnitude of this? 35. The magnitude of 35. Go Wolfram Alpha. Tell me something. What does it tell me? Okay, it's giving me its forms. It's got a real solution. Let's see. Those numbers. Wait a second. What we got here for numbers? 1.6162. 1.6162. A little further. 273. Oh, that seems to be right at about 1 sigma on the top end of the Planck length, my friends. That's 35th power. This is related to a 35. Now again, it's just if one was to look for hypothetically closed forms of the Planck constants, how would we even go about it? Maybe trying to use the base of natural logarithms might be a step. Okay. So what we're going to do this. I know Thad likes the hyperbolic sign of the hyperbolic sign, so now we're using the same thing. And, that's probably the best way to do it because once you have a thing, you can just keep on using the same thing. That's fine. It makes it less complicated. But for what we just went through there, and just for ease of this notation, it's the cotangent, aka cot of 1/7. 1/7. That's E. We're solving for X. That's equal to 35. Leads us to 1.616 times 10 negative 35 meters. Cool. All right. So if we haven't detected a pattern yet, this is basically the pattern. We just keep on doing this. We go through our iterations and everything. And yeah, we basically just continue doing this. Why? Because, well, if it seems to work, and apparently it's hard to tell. The internet is a great thing. It's also its own worst enemy. In that the great part about the internet is because it helps give a voice to the masses. Basically anybody that has a generalized internet connection and stuff like that can get out there and speak their mind. What's the downfall? Anybody can get out there and speak their mind, and especially certain personalities may lend themselves to spending a lot of time on the internet and talking a lot of smack. I'm not saying it's a good thing or a bad thing. I'm just saying it's a thing. So since that is a thing, um, usually a lot of loudest people drown out other folks. Apparently, at one point, Thad was like, "I think I found it." He puts it on like Facebook, and he gets all excited. And, oh, it's some little interaction. It's like do 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 do, and it's like, okay, well, that's fine. I'm going to keep on doing some work. Why? Because you're good. And if there aren't people actually trying to work on these things, maybe trying different alternatives, because it's not like it takes the graduate professor of student studies at like Harvard University for physics to come out there and be like, so we don't actually need this axiom part over here. Like we can actually broaden it. You can keep your Hilbert space if you want, but just understand a generalized configuration space would work. And as long as you have a unitary stochastic stuff, things seem to work out. I'm just looking, I'm like, okay, I know a lot of people come out pretty much every other day. It's like, I have solved all this. And every once in a while, it's like, look into this. And it's like, I mean, your numbers don't matter. Like, it's not even the right magnitude. It's not it. So it's like being able to differentiate the crazy people from those that may potentially be crazy enough. It's hard. It especially so it's now with a lot of the LLMs, you just let me toss an idea. Oh, it says like, I just solved everything. Yeah, I have it tell me that all the time too. And I'm just like, yeah, but it's probably really, really. I mean, is this worthwhile? But go over check boxes. It's useful tool again. The right tool for the right job. Probably again, generalized search and probably write things yourself. Just personal opinion. Uh, where are we at? Okay, so we did that. All right, charge. Oh, well, charge isn't even listed there. Let's go to. We'll just go to Wolfram. To like church. And our friend over here. Yes, Rick. That we must define crackpot before we begin speaking about those things, because I think often it comes down to I don't like that person more than it necessarily should. But oh god, you make me want to play. Well, wait, I need to do this first. All right, so let's take. Okay, and again, probably have a disagreement with Wolfram on this. Okay, but we're gonna go to charge. We'll just do this. Delete this part because bracket that because that's we're raising our good friend E2, and then we're just solving for X. We throw an X in there, and that was of the magnitude 18. So 18 magnitude. Let's solve for that. Let's see what we get. Ooh, it's very pretty. Uh, ooh, Oh, that's a pretty number. Let's look it up. Okay, so we got some stuff there. If we got any more things. Oh, we might even have better answers over here. Who knows? But then again, whatever you got, you need to make sure it conforms with the data. Okay, so I'm not really sure. I think this was a hard one. I think we needed to search a little bit more. Let's see. Because the best answer that we had, computation live. Salem constant. We got our goat friend there again. Yes, Hex. Yes, Hex. Oh, Hex, you have prompted me. For those of you that don't like Ren and Stimpy style little catchphrases, this may be a little loud. Okay. You've been warned. Why? Because
Come on and get your log. Everyone needs a log. Come on and get your log. Everyone needs a log. Log from Blammo.
I am a child. What is that whole thing? Know thyself? All right, let's take out another digit here. Let's see. Like it was, because was it our answer has a deviation, I think around the 6th digit with Wolfram. I think. Okay, what do we have before we had an 8? My standard thing is let's do this. Let's do a 5, because sometimes you got to search the territory, because it's only going to give you so many things, and then it's like, all right, delete a digit. All right, anything 0. All right, 2. All right, 5. All right, 8. Sometimes you need to literally just go, oh, it takes so much time. God bless that. And it's we do have an automated process too that Avi, shout out to Avi, it's set up, but oh wait, no, we already had an 8 there. Yeah. Go down to 2. What was the last one? Was that 2 or 5? 2. No. So let's see here. Eh, eh, eh. All right. The actual grinding part. Hold on. Oh my God. I'm not even sharing. I'm just rambling on and making weird sounds. But then again, how's that different than the rest of humanity? Let's see. All right. So we had that. What did you grab? I think Planck length. Planck. Constants. No, 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 no. That. Like units. There we go. Did they charges beneath this? All right. I think that looks 987 5546. So 5 6. Okay, so let's do that. Da, 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 da. 5 5 4 6. All right, let's try this guy. E raised to that, solving for x. That was of magnitude 18, negative 18 coulombs. Okay, because it's the exact same dang number. All right, so long story short, we get out this friend here. So this ends up being, what are the numbers that I need? Numbers that we need, 5882. Oh, I just need to add digits. Oopsie. All right, so we'll just do that again. All right, boom. E raised to that. X, boom. 18. I probably should have checked while I was playing the log commercial. Oh well. C'est la vie. All right. So, all right. So we have that guy. Again, we're cheating. We're cheating. We skipped ahead. I'm adding a 2. I usually add 2 when looking for stuff anyway. I might even need to add more because I think this was a tricky one. Actually, need to go out. Yep, need to go out more. Wow, how many more digits? Do 7-3. Okay, I'm doing the whole 7-3 because that was very annoying. Because I remember looking for this dude once, and it was just like, how many digits do I actually need? Here we go. All right. So again, this is maybe there are other answers, but at least what do we got here? We got 5-dimensional ingredients of reality. I'll just by base interpretation, divide by the cubed root of 3. There's the square root of 7. There's the Weierstrass constant. Oh, that's the simplest fractal. Oh, I think I have. Hold on. Where is it? I'm not going to say this is necessarily a. Oh, maybe it is a. Can you call it a meme? I don't know. It's here we go. Oh, the Weierstrass function can. Here's how I remember it being what it is. The Weierstrass function goes up and everything has these peaks, and it's a very distinctive peak because when you look at it, the peak ends up looking kind of like this. Yes, I remember it as the wizard function. Just because you can fit a wizard with a pointy hat within its. I grew up. My grandmother, God rest her soul, she had a place in Florida, and in the guest room, it had these decals on it, and I swear it looked like the Weierstrass fractal. And I always viewed them as just like these stern old wizards, just being like, "Don't you start any trouble, young man." I still started trouble, not as much when the wizards were watching, but I digress. Yeah, it's the Weierstrass function. It's basically the simplest fractal. But all right, so we got that dude. So if we take this dude. All right. So we copy that. We go into our little friend here, blah, blah, blah. All right. I need to type it out. Where? Press function. Make sure it actually understands, even though I'm sure I spelled it wrong. Wow. I don't. Okay. I'm just going back. There. Where's stress constant? That was the total thingy. What are we doing? Oh yeah, multiply by e. We're going to solve for x, and that was of the magnitude 18. Now note we are going to have deviation here. There's going to be deviation. Why? Not just because I said so. That's stone cold saying. We're going to get some more digits here. But there may be a very interesting reason why, and I think, do we have time? Yes. Okay. So let's just go to Wolfram Alpha. What is this guy? So go to Planck charge. I'm not even sharing my screen. I apologize, everybody. Planck charge. Window. Boom. Share with the people. All right. All right. So we got 1.8755. All right, let's see what we got here. 0.8755. Okay. 46. 45. That's a 9. So that's pretty close to 6, and that's where we get our deviation. So 1, 2, 3, 4. So basically, if you took the total significant digits, 1, 2, 3, 4, 5. So basically 6. Basically on the 7th, right around the 6th, 7th significant digit, we have a little deviation there. Okay, and that's related to a power of or an 18 thing. And okay, yeah. -18, so of magnitude 18 coulombs. What is Wikipedia? Okay, so they basically just stop it right there. Okay. And Okay, and it's 6-0, so we had a 5-9 in there. Okay. So it's kind of close, but again, there is a deviation there. All right. So why do I bring this up? Why do I say this might not be a problem? Okay. Because if you take that, you got that coulombs there. All right. So let's zoom in. And then if we take let's do this. Square root. Find structure constant. We're gonna get this. This, my friends, it's basically Joe according to basically the current settings of the fine structure constant, which we also have a deviation from. It's actually one of the strongest ones. It's 7.5 sigma. How the heck could we justify that? Oh, let's justify, my friends. All right. So we're going to bracket, and we'll take our Coulomb number there. Okay. What do we get here? 1.602 times 10 to the negative 19 coulombs. That's a pretty small number, my friends. All right. What's that? Let's go to more. Oh, look. That's one elementary charge, my friends. Okay. So it's literally that is the current definition. Okay. So riddle me this. That was our Joe friend. Let's take our number over here. What do we get? We get down here. Copy that. Throw it into our thingy over. Where do we put it? Over here. Okay. Plug it in. Plug it in. Okay. Let's see. Okay, it's a little bit different because it's still going to tell us it's right. It might be too close, so it might. Okay, see, look, we have deviation here. Yes, 1, 2, 3, 4, 5, 6, 7. On the eighth digit after the decimal point, we have a very slight deviation. Okay, can we fix this? To be fair, I'm not even sure if it's going to show it's going to fix us, but let's do it anyway. Will I epically fail? Probably. But let's go over to our friends, formerly known as the hyperbolic vortex equation, currently the hyperbolic partition equation. Okay. So again, this is our good old friend 1 over x plus x cubed divided by 2 pi set equal to I raised to the I, should technically be I raised to the j for orthogonal descriptive purposes. And that's raised to the negative pi divided by 2. And then this is the absolute magnitude of the Planck mass. You could throw the Planck mass. We're getting ready to derive that in a second. And basically, that's where this number comes from. Okay. We get our Joe right here. Okay, let's grab that. This is basically the square root of the fine structure constant, or its amplitude. Let's go over here. Where was the... Oh, we had to go back, don't we? Okay. So rather than the square root of the fine structure constant out into that, we're going to put this in. Boom. We're going to hit enter. What's going to happen? I don't know. Let's see. Oh, look. We get it equal to elementary charge again. Wait a second. We're doing something that had the last couple of digits differ from the currently measured form of the fine structure constant, and it deviates from the Planck charge listed on Wolfram alpha, but we get the same elementary charge, my friends. That's why we may actually have an explanation. Again, we could be wrong, but this might explain a few things. Again, don't trust me. Look at the calculations, play around with it yourself. Maybe there's a tragic flaw. I originally thought it was a tragic flaw, and then I saw, I'm like, wait a second, the weakest part of the model might actually be one of the strongest parts, because you don't need to use our model to use these numbers. If these numbers help you for whatever you're doing, please use them. One goofy man they float, isn't that the goal? All right. That tangent aside, wanted to do that for a while, and I did it once and it worked, and I wasn't sure if it was actually going to work again. It was going to be a rounding thing. Man, that would have been embarrassing. But it was lightning. All right, so we did that. All right, so let's go through. Let's do our same thing again for. All right, we need the Planck mass. Now we can go back to our friend's code data, and we can maybe speculate a little less. All right, Planck mass. The Planck mass according to code data. We got these digits here. Boom. We go back here. We do our standard. We're solving for x. We're using the power of log. Do, 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 do. All right, we raise it to that string of digits. And then the Planck mass is what? It's 10 to the negative 8. All right, so that's 8 magnitudes. So we're just going to set equal to the magnitude of 8. All right, I guess we get a solution over here. All right, we get that little solution. Let's see, is there anything that sticks out to you? Oh, that looks like a pretty geometric thing. Seems to get almost all the digits. And that also happens to be the thing that we're using. Why? Because we can just copy and paste this. So basically, I'm just reading that as 10 circles, cosine squared, 7 divided by 5. Oh, we've been seeing some 7s and 5s pop up. Oh, very interesting. You can also rewrite it as this, but I'm just going to just delete that. I'll put it in. So I'm making sure that I'm not up to any funny business. I love getting up to funny business. But for here, I'm going to multiply that by e. I'm going to solve for x magnitude. And we're saying that equal to is a magnitude of 8. We hit enter. We get our thing. We get our circles there. Bada boom. Bada bing. You can rewrite these other ways. We get a real solution. Now, again, I've been ignoring some of the other solutions. We'll get into that more later. Those are like wavy stuff and things and rotations. I think you're gonna like it. All right, what do we got here? 2.1764. Got here. 2.1764. Hold on there. 64268. 234. All right, error bars are 2-4. Oh, well, it seems to be as it last after the it's 434. See over here, it's 426. 426. Oh, that seems to be well within the error bars there of 1 sigma. How very neat. And okay, for those not paying attention, the actual solution, you multiply it by I. What's this? Oh, that looks like a 2 pi in there for n. What is n? Insert your numbers. Perhaps, I don't know, if we had something with the integers, something that maybe allowed us to count, that would be very useful, I claim. I'm sure many other folks claim that, and probably a couple here watching now or temporally in the future, but we shall see. Okay. So, oh, I skipped over. I didn't even write on the board. I'm a terrible YouTuber. All right. So what we have for this is, I know. It's as empowering as screens are. It's nice to relax, stretch, do some other stuff and things. We probably should do some more handwriting stuff. I think that's pretty fun. That's also my worst subject. Okay, so what are we doing here for a closed form for charge? How are we writing it? Let me go here. All right. All right, so we had a friend 5 again. I know, seems to pop up all over the dang place. We had 5, and then that was, oh yeah, the cubed root 3, square root of 7, and we got WWE, not World Wrestling Entertainment. Oh, why stress function, my friends? Am I just realizing right now it literally is WWE? It literally is WWE. I love reality. And we set that equal the magnitude of 18. I'll give us our good friend down here. 1.8755. 1.8755 times 10 to the negative 18 coulombs. That's a cool word. Also somebody's name. That's why it has that name. All right. So we got that. And we had the Planck mass, which is our other friend over here. So basically we got 5 circles, aka we got 10 pi. Pi. And that's cosine squared. Cosine squared. Oh, I forgot to put the c to the x term. E raised to the x equals. There we go. All right, it's cosine 7 over 5 over 5 e to the x, solving for x. This is of a magnitude 8. That should give us 2.17 64. 64 times 10 to the negative 8 kilograms. Okay. So we should also say at least claim, and again, the power of this, sorry. Basically, what I'm writing right there, that's nothing new. You can get that on Wolfram Alpha, you can get that on Codata, you can get that from pretty much wherever. It's the benefit is, since these are claimed geometric closed forms for the Planck constants, you can take as many digits of these as you want, because when you hit more digits on Wolfram, like it gives you basically right here, it's probably about 14 or 15 digits when you just hit more, and then you just do more digits, and you can just keep on going. Now, you may only need like 14 or so, but hey, it's not a bad method to, let's just say, have a educated guess about what those other digits are. Now, in order to actually try to verify that, you're going to need a very well-formed, coherent theoretical framework, preferably supported by experimental verification, or at least evidence voting in one's favor. Okay, you want at least a couple more confirmed predictions in string theory. I don't want to hate. I'm sure string theory has its place in everything. Maybe it's ribbon theory, maybe it's this, that, or anything. And listen, if it's a beautiful mathematical model, hey, you do whatever you want. I at the boss of nobody. But all right, our last friend, and we'll wish everyone a happy Thanksgiving, and then we will close this out in just a moment. Blank temperature. All right. So again, we're going to do our same little thing here. I'm just going to copy a string of digits. Be a savage person and just do x, e, raised to this string of digits. I'll close the parentheses over there. And this was at, 10 to the 32 Kelvin. That's very hot. All right, so magnitude of 32. Searching. Get some numbers. Get a solution. We click solution. And we look for cool stuff. Oh. Let's look for some geometric closed things that, it's at the lurch. Let's try something. Oh, that's very interesting. We're getting some new things over there. Okay. I don't think that's what we're looking for. What are we looking for? Oh, we're looking for that one. Okay. I'm just literally looking at what it is over here. So not that I have all these remembered. Oh, that's actually kind of cool too. You write that as 18. Well, then that would go to 20. Bum, 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 bum. This is one of those tough ones. Hold on, let me skip ahead. Let me cheat. Let me look for what we're looking for so I won't bore you all as I'm arbitrarily looking at the landscape of places. Give me need solve for you. Solve for you. It gives us okay. So where we 5, 9. Da, da, da. Go over here. We have there's some other pretty friends here. Which what do we want? 7, 5, 9, 7. 7. And then that's 7, 4, 0. 4, 0. Boom. Search here. People need to hold me to account. Okay, I'm finding other pretty thing. We'll just 7, 4, 0, 6, 8. 6, 8. 7, 7, 5, 9, 7, 7, 7, 7, 5, 9, 7, 4. I found. Oh, I made a mistake. After that 7, there is no 6. That is why. Boom. Okay. Let's see. 7, 7, 5, 9. 7, 7, 5, 9. 4. 7, 4. Tubsy kitten. There. 7, 4. 0. 6, 8. 6, 0, 5. 6, 0, 5. This friend does not want to be found. Wow. You're hiding real good. I may have also just completely gotten this wrong here. Here's what we'll do. I'm going to cheat because my eyesight might just be going. We'll do this. Paste you in here. And we'll delete from there. Okay. Let's see. Maybe we need more memory time. Could have sworn how many digits we need. It might just be in a form that I'm just not recognizing. Oh, the struggle is real. Huh? Go through this really quick. But being you said it, Rick, and it wasn't me. Let's see what we got. Da-da-da. Yes, this is much of what this is. Literally just going along. Search real quick. Glance, more, click. Is it good? I feel like I just wrote those wrong, and I just misinterpreted what it was. It's okay. We're skipping ahead digits. I won't pain you with a search of every single one. I want to show that it will pop up. And if it doesn't, I feel like we've at least proven a lot of our case here. This is okay. So maybe it requires a little bit more searching, or maybe actually, I think we can just rewrite those. Just go down to here. Bum, bum, bum. Wow. The algorithm is crazy. It's like I'm just sitting here searching. It's like, oh look, let's bring more people in. Why? They like watching a screen that's loading most of the time. The algorithms are a silly thing, my friends. All right, so long story short, okay, ultimately you search long enough, you get this friend. This friend comes in here, you do the E, raise to the X that was of magnitude 32. Bada boom, bada bing. You get that. Okay. Approximate form. Oh, what are these digits? 1.416. 1.416. There, 6, 7, 8, 6, 9. 7, 8. Oh, 4. Well, that seems to be well within the 1 sigma of the Planck temperature, my friends. Just because we're using another geometric form that has what? No, that was mass. This temperature. We got 2 hyperbolic cosines. Log of 7. Oh, that's what it was. It was the log function over there. It's just rewritten in the other way. Okay. And then the cosine of 5 over 2, blah, 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 blah. Yada, yada, yada. Okay. Cool. So that's all the potential magic for right now. Oh, I should probably write it on the board. Let's where was it? I think it do this. All right. So we get 2 cosine hyperbolic log 7 it's squared 5 over 2 squared 7 over 5 and e to the x. And that gives us, set that equal to 32. Leads us to 1.416 times 10 to the 32 Kelvin. Okay. So that's the process. And hey, if we have some closed forms for some building blocks of reality, maybe we can get a little bit more real. But other than that, take care of yourselves, everyone. Have a happy Thanksgiving, and it's the wacky wild world out there. It's open for the guest. Peace out, everybody.